video. Hello, I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller of CME Computer and IT Solutions.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and 2 p.m. on Saturday in Queensland, Australia. We're broadcasting live from Thousand Oaks, California. Thank you so much for being here. We want to start off by saying congratulations to the Vera Rubin Observatory. It came online and had first light last week. I'm going to share this real quick. And there we go. This is from NPR. And look how beautiful. And that's just the beginning. Can't wait to see what, in fact, we learn from this powerful new telescope. Apparently has the biggest camera in the world.
And they stack a bunch of photos too.
Oh, I did not know
that. Was 670 some
that's right.
Photos.
That's right. And you've got some cybersecurity news?
Yep, but first, hi Scott.
Oh, hey Scott. Welcome. So we gotta move this one. There you go.
Okay, some cybersecurity news. This time from Canada. Apparently, some Chinese threat actors have decided to compromise a whole bunch of telecommunication companies. Now, some of these companies are international, so I don't think the threat is just against Canada. I think it's a widespread threat. It's just that Canada is reporting it right now. So your email addresses and passwords, if you are probably compromised. They probably have them. So I would recommend changing any of your passwords that are related to any of the telecommunication companies, because we don't know if they did more than just the ones in the three majors in Canada.
So you're talking like T-Mobile?
Yeah, that sort of thing. Yes.
What are some of the other ones? I don't even know
Spectrum.
Anymore. Okay.
Spectrum, Frontier, T-Mobile, Verizon.
Right, Verizon.
I mean, basically any of them. I would really recommend getting rid of, changing your passwords up. And I do have that URL here. This is the URL for that report. So if you are interested in the details, they've got a lot, and they've got advice and guidance. Basically, that's what they call, their recommendations.
Oh, that's good. That sounds very useful.
Yeah. So if you're in Canada, definitely look at this. If you're anywhere else in the Americas, it's probably a good bet to read. And if you're anywhere else in the world, you probably do want to see this, because, like I said, I don't think that they're just concentrating on Canada.
Yeah, it would make sense that they would hit more places.
Yeah. So
we've got a couple more comments, I think.
Okay. Nope, that was Janie.
Hi, Janie. Hi, Janie. Welcome. Looking forward
to the
yes.
Yeah, the photos from the telescope. Yeah.
I've seen a couple, and wow.
Yeah, but they will be slow in coming because they do stack the photos, and so that's a composite of, like I said, 670 something photos. So
I do remember reading that.
Yeah.
But it didn't occur to me that it was stacked. So
yeah,
that's the term they use for it.
Yeah, they're going to be slow in coming out, but they're going to be glorious.
Cool. Everyday Spacer is sponsored by CME Computer and IT Solutions.
Tonight's show is about kitchen table experiments. We'll be back in 8.3 seconds. There's a link to that book in the description. If you want a signed copy of the book, write
there it is.
Write that. Pam at everydayspacer.com for details. Oh, hi, Naomi.
Oh, hey, Naomi, welcome.
Hi, Dawn.
Glad you are here. Glad you could join us.
Yep. So, what would you like to learn next? Would an experiment help? Do you already have what you need to conduct that experiment? This week, we'll explore ways to look at normal things in your home as potential tools and supplies in the pursuit of your next experiment.
I missed a line. You can go ahead and say, Pam, why don't you take over?
Pam, why don't you take over?
Or whatever you'd like to say.
Or whatever you'd like to say.
Sure.
Sure.
All right. So tonight, I'm going to talk about things you can do at home with science experiments, that kind of thing. And where did I start first? Kitchen table experiments on Pinterest. And well, I thought we should start with food because, of course, food. 15 kitchen science experiments you can eat. And
I know you can eat Play-Doh. That one in the top corner looks like it's balls of Play-Doh.
Oh, but these are special.
There's special balls of Play-Doh. I
yes. Because they have spices involved. That's what I read there before anyway. Oh, okay. So, and this one is in particular talking about it's summer and your kids are on break, but don't let that stop you. You do not need a child chaperone to do experiments in your kitchen. All right, Avada Kedavra. We'll simplify this and make it a little more readable. Sometimes the ads interfere. And I think this is going to be sort of a compilation, and it'll point you to a whole bunch of other websites that have the actual experiments on them. And, you know, you can stay busy with your kids, but you don't have to do that with your kids. You can do it yourself. I did think these were pretty creative, though, because like this first one, make a cake while talking about layers of skin. And they point you to the website. Then you learn the science behind edible glass. I'm thinking that one's this one. I don't know where the candle comes in, though. Making butter and whipped cream. That's pretty interesting. We got a comment?
Yep. Scott says, I once experimented by putting a raw egg in a microwave. I discovered quickly that that was a bad idea.
So with the shell or in a bowl?
Well, in the shell, it basically overpressures as it boils. It makes a big mess of the inside of the microwave.
I bet.
Cliff says, hi, Cliff. He says, hi, guys. Food, glorious food.
Food, glorious food, yes.
Yeah, Scott, I once learned what happens when you dry boil an egg.
You mean like...
Let the water evaporate out, and then...
You had to find them on the ceiling, I bet.
Yes, because it didn't like explode. It cracked. So every time it overpressured, there'd be a spurt of egg that would hit the ceiling. And then,
I saw a lava video speeded up like that, and I guess it's going on in Hawaii.
Yeah.
Okay, there's an experiment for you. And of course, there's biological experiments in the fridge.
And then, of course, I did take it off the fire. Then when my mom came home, because I was, a kid at the time, she asked, why did you leave it on the ceiling? My answer was, because I wanted her to see it.
Okay. So she must have been very tolerant of you.
In the shell, it exploded.
In the shell, okay.
Yeah. Well, my mom wasn't necessarily tolerant of you, because when I said, because I wanted you to see it, she went, oh, that makes sense.
Tolerant, like I said.
No, because she would do the same thing. So it says, pin in the pointy end of the egg and it won't explode.
Oh, good to know.
All
right. Rock candy is good, and I think that's kind of cool because in my world, I have a degree in electronics. You find out about things like dropping, for cells, the chips. You can just have a drop into, I guess it must be molten, right? Mm-hmm. And it will do the same exact thing as this rock candy idea, right? Isn't that how they work? Mm-hmm. Okay, so
chips
sorbet
what,
was what?
You said drop chips.
Yeah, I forget what it is.
Okay.
I got that degree in '85, so it's been a while. And okay, make sorbet with snow or ice. We're not going to find much snow or ice in naturally here in Southern California. But there's ice in the freezer.
If you go high enough in the mountains, yes, you can.
Yeah, I've never been there.
Because we do have glaciers here in Southern California.
Yeah, it just looks pretty over in the distance. I've never actually been there, so it could be a picture. I don't know. All right. So, find out what keeps an apple from browning. That's pretty cool. You can make popcorn with an ear of corn. Oh, they actually have a picture of that.
I know what makes an apple not brown.
Yeah.
Eating it.
Yes. There's the picture with the corn cob in the microwave in a bag. That's different. All right, so we'll go back to the ad-free version. And they talk about coloring celery, and I think that was really, as we saw, I thought there'd be pictures here. The celery put into
them with the ads.
Yeah, probably with water with food coloring in it, that kind of thing. Yep. I see a comment.
Oh yeah, because it'll. I burned up an indestructible Revereware saucepan with an egg in it.
Wow.
I'm no longer allowed to leave the kitchen when something is on the stove.
Okay, that sounds like a pretty good rule. Edible bubble science with apples. Huh. Okay, that's a new one on me. Lemons and make fizzy lemonade. Okay, and learn to play with it. You can have slushies with no blender. Oh, I want to see that one because I think I've heard about that. It's pretty much ice in a bag around it. Anyway, if you go to these websites, they will tell you more. Actually, I want to see that one, so maybe that one too. Let's go look at these two. Just cause. This one. This is the. All right, so let's see what they show us. Edible bubble science experiment with apples. Okay, let me bigify this a little bit. Smoothies for snacks. I just like to drink them, but she likes to use a straw. Okay, bubbles. See, there's a good mom. I decided to capitalize on that obsession with an apple-themed bubble science experiment, and of course it's edible. Our very popular pumpkin bubble experiment uses normal bubbles, but I found that really young preschoolers and some older toddlers love to blow bubbles too. So I designed the science experiment for them. What does she put in there? Apples, orange juice, milk, straws. Wow, that sounds wild.
Oh, the milk is the surfactant.
Is it?
Yes.
Okay. So pull the core out of the apples, but mixing them together. Orange juice. They can blow bubbles in the orange juice. Okay. They'll pop quickly. Okay. I guess this is to compare and contrast between the different things. Okay. That makes sense. Then the milk. Okay.
Yeah, the milk blows good bubbles.
Again, the surfactants thing. And that's just the word for. What does that actually mean? Is it they stick together or make bubbles or?
Yeah, the surface tension. They have a lot of surface tension.
Got it. And okay.
We used to blow milk bubbles too. And and your comment about my mom being very tolerant.
Yes.
Maybe.
I don't know if I want to know the rest of that story. All right, so that's pretty cool. And there's a lot of stuff in here. All right, so let's see. Slushy science. How do they do that? Without a blender. Okay. I'm going to bigify this one a little bit too.
If you've got some liquid nitrogen
and well, I don't think that's
in
your
a supercritical point.
Most
you can slushify.
Most people don't have that in their kitchen. Okay, magic ice cubes. Oh, night before you want to make a slushy, put half a cup of water and 1 teaspoon of salt into a plastic bag with a seal. We had a food coloring just for fun. All right, so there they are. So it's inside the jar. Okay. And when the bags have frozen, put them into a jar with a lid and add a cold liquid. We use fruit and vegetable juice. Anything with sugar in it will work. Okay. Don't pour too much in. We use 6 ounces of juice for each bag. Start shaking. Okay. So basically the cold from the ice pack transfers to the juice.
Right. And the salt in it makes it so that if it's frozen, it's frozen at a colder temperature.
Yeah, weirdly, adding salt makes it colder before it melts it, even though salt is used to melt ice and snow. All right. Yep, here it is. The salt lowers the freezing point of the water in the bag, so the bag of ice stays colder longer than plain ice. This is what causes the liquid surrounding it to begin to freeze. Very cool.
And the shaking of it breaks the frozen liquid away from the bag. So you're constantly making little small bits of ice.
Okay. All right.
We used to have
Cool.
cup liners that you would put in the freezer, pour stuff in them, and then just continuously scrape, and that would make your slushy. So that's the same concept.
And when I was a kid growing up, we had an actual crank ice cream maker, and they would put ice cubes and rock salt around it. And then we cranked and cranked and cranked and cranked. And even then, it came out kind of soft. So let's see. They got here's the pictures. There it is. Make homemade herb and spice Play-Doh. Edible slime. That must be this one.
Since the kids are going to eat it anyway, yes, might as well flavor it.
And experiment with gummy bears. What the heck's that one about? Let's take a look at the gummy bears. Oh, I guess you're going to saturate them with liquid. Something like that. Growing gummy bear science. Here's the gummy bears, and there's what after water? They do water? Water, salt, and gummy bears. Okay. Okay, salt water.
Water versus salt water.
Oh, I see.
I think it absorbs the salt water more.
Okay, yes. Yes. I see what you're saying. Super saturated. So, okay. Oh, I see. So here it is. We added salt a little bit at a time to a cup of boiling water until no more salt dissolved.
The boiling water would make it dissolve faster.
Well, and they enable more of it to be dissolved.
Yeah.
Use caution, yes, especially with little ones. Even for yourself. Once the water couldn't hold any more salt, we let it cool in the fridge. If you use warm water for your experiment, you could melt your gummy bear. I see. You do want to have a gummy bear at the end. Okay. When it cools, it's time to fill the bowls. A little salt water in one bowl and plain tap water in another. The gummy bears in. Oh, they have to be similar size. Okay, that makes sense. All right. And you'd want control too. So you placed a couple gummy bears in the salt water and a couple in plain water. They wanted to eat the remaining gummies. we need them for controls. Good, Mom. Because we want to compare, see what happens. So we know what the original looked like. That's what the control is about. Okay, in they go. And now all we had to do is wait. And I think you could do some other things too, like timing. Which ones would go faster? Which ones would go more? Which would they make bigger? I see a comment over there.
Oh, Janie. So Janie says we had to take turns to turn the crank of the ice cream maker. Delicious peach ice cream. It melted so fast. Yep,
we do too. And I mean, there's some electric ones, but this one was a true crank.
Yep.
And it looked old even like when I was a kid. So
and
super.
If you think about it,
vintage.
It doesn't make it super cold like you get out of a freezer. Plus, if it's ice cream weather, it's going to melt.
Yes. Oh, you got to let them soak for several hours. Oh my goodness. Not overnight, though. They might fall apart. My 5-year-old, oh, this is good, predicted the gummy bears in the plain water would expand and the ones in the salt water would shrink. That's great. So that's a hypothesis. Yay. This is what we found the next, well, they did leave them the next morning. Oh, look at this. That must be our control, right? And that's a really big one. So which one? The yellow bear was the control. The red was salt water. And the green one was soaked in plain water. Okay. It doesn't seem smaller to me, though, the red one.
It did. So it did soak up some water, but the salt was,
Probably couldn't get into because the salt grains would be bigger, maybe. I don't know. Both were surprised to see how much bigger the bears soaked in plain water had become. They noticed the bears soaked in salt water were a little bigger, but not that much. Oh, boy. The kid ate the saltwater gummy. He was surprised when it was salted. Okay, so the salt did get in. The science behind growing gummy bears. To make gummy bears, sugar, gelatin, and flavor are dissolved in a warm water solution. As the solution cools, water leaves the gelatin solution, and the bears become firm but chewy. Not all water leaves the gelatin. However, otherwise the gummy bears would be rock hard. Okay. It is this little bit of water that makes the gummy bears act as a solution of water, one with a lot of sugar dissolved in it. Okay. Okay, the water in the plain water had very little dissolved in it. Oh, and they do an egg experiment too. That's cool. That dissolves the shell. Oh yeah, I've heard about this.
Mm-hmm.
You put an egg. It must be hard cooked, right?
Yeah.
No, not necessarily hard cooked. Into a thing of vinegar, and I think you wait overnight.
Yeah.
And it becomes bouncy. Okay. Yeah, the water with very little dissolved in it will move toward the solution of water with a lot dissolved in it, the gummy bear. This movement of a solvent from one lower concentration to a higher concentration is called osmosis. So that's what's going on there.
Mm-hmm.
Of course, you're telling the kid that, right?
Mm-hmm.
Yay. The force behind that movement of water is called osmotic pressure. In the bowl of salt water, we tried to balance the amount of salt dissolved in the water with the amount of sugar dissolved in the gummy bear. Since our gummy bear placed in the salt water solution did expand a little bit, we knew our salt water solution did have a lot dissolved in it, but not quite as much as the gummy bear did. Okay, so that's pretty interesting. I guess it was a pressure difference. Is that what I'm reading?
Yeah, partial pressure. It's just water or any other dissolved or any other liquid will go from a higher concentration to a smaller concentration.
That makes sense. So a little water moved into the gummy bear to balance the two solutions.
I think that's it for that one.
Yes, and there's more. Walking water. Oh, I see. Okay, so for a long time, I have really wanted to understand how you determine your latitude and altitude. And boy, did I find out a lot of stuff, because it's not as easy as I thought. Now, if you're in the northern hemisphere, it can be relatively easy in the night if you can see Polaris. You just kind of measure the distance, and that's your latitude, right? But you can do it also with, and I'll give you this link too. This is a pretty good video. You can do it with the sun. And that's where it gets a little tricky and involved. Let's see. Hang on, let me get to you. All right. That should be a clickable link in YouTube. Looks like the Facebook pages have again failed. All right. So, if you have some regular old tools, that might help. But what I really wanted to know was this one. Can you actually build something like that? And it seems like it's possible. You have this straw, and let's see, they call it. Here's the page about it. Yeah. How to determine your coordinates, latitude and longitude without GPS. Now, I was really interested in latitude. Longitude, probably interesting. I didn't care as much. But they do have both here, and a couple other pages have both as well.
You generally need a watch for. You need to be able to tell the time for longitude.
Yes, that's what I understood from, I think, later on in this one. Now, this is kind of interesting, too. They are in the UK, and they have a mobile star dome. They travel all over to bring space science to our learners. There are sat navs to tell them, but if that didn't work, you can learn to do it for yourself. Okay, so on Earth, we specify one's position using latitude and longitude. Yeah.
You might want to get rid of
that. Yeah. Or you could.
Oh, yeah, I guess I could.
Sorry. Wow.
There you go.
Okay.
Just I usually handle comments, and you usually handle panels, so
The latitude runs horizontal and parallel to the equator. No, that doesn't sound right.
Yeah.
Latitude.
Yeah.
It's longitude that goes around the poles.
Because the lines are longer, that's makes it longitude.
Ah, got it. Okay.
Not really, but it's a good way of remembering it.
Okay, I like it. All right. So let's see. The longitude lines are meridians, run vertically. Yep. So they cross the equator at a 90-degree angle. Got it. Okay, good stuff. Every point on Earth lies on the intersection of a specific parallel and meridian. Its unique coordinates, and consequently, this is also true in the sky, in the night sky. They've expanded that, but they call it something different. It's right ascension and declination. And I think we've talked about that before, right?
Mhm.
How to find your latitude in the northern hemisphere only. Unfortunately, there is no visibility of Polaris in the southern hemisphere.
There's dirt in the way.
Yeah, it's a lot of dirt. So yeah, I guess it's because when you notice that when you move south, the North Star appears closer to the horizon, and when you move north, it's higher in the sky. And interestingly enough, when I came out here to California, I was sort of surprised because in my world, the Big Dipper was always in the night sky because in Ohio, it's a much higher latitude and it never goes below the horizon. Here, it does. It's still kind of weird, but I know it now. I'm used to it. So let's see. So I think this little tool is what they help you build to see. Yep, there we go. This is a picture of it.
So that kids can ruin their eyes
No.
before the age of 12.
Well, no, you're looking at Polaris. You're not looking at the sun.
That's not a sun sighter. That's
no,
a Polaris sighter.
This is for Polaris.
Oh, okay. That's not nearly
And
as interesting.
they have a term for this this PCR. That's what I was looking for. Maybe it's below. Yeah, if you do this, don't look at the sun directly. There are indirect ways to do it because you can use the sun. So here are the components. It's a straw in this piece and a weighted string. Let's see, a quadrant. Here we go. Quarter of a circle. And here's the word sextant. It comes from a sixth of a circle. And there is, in fact, an old-fashioned tool. You can actually get some modern ones too, but the old-fashioned ones are like brass and really cool looking and stuff. They've been used for navigation for a very long time. And you can make one yourself.
And they only need a sixth of a circle because Polaris will only get so high in the sky.
Mm-hmm. At night, look through the viewer. This is the straw part of it to find the North Star. Then read the number the string will weight with. So you have to actually create this and put them in the right places, of course. Now, let's see. Did I say yes? You can make one yourself. I'm going to go ahead and pull up that link. At night, look through it and find the North Star, then read the number because the weighted string will be crossing that point. How to find the longitude? Yes, here's where they talk about the watch. Figuring out your longitude will require a little bit more work. You need a clock, a phone, a good friend at Greenwich on a sunny day. That is a lot more work.
Well, your phones have watches on them.
But they say you need a clock and a phone. So I don't know why both. And a good friend at Greenwich. So I don't know. We're gonna have to look at that a little more thoroughly. Because I'm not sure. Oh, I guess the phone is to call your friend in Greenwich.
Yes.
Hello. All right. And it has to do with local noon. Mm-hmm. All right. So that's kind of an interesting concept too, because every day it's at a slightly different. Mm-hmm. Well, it's in the same position, but it's a slightly different angle in the sky.
Right. Yeah. Okay. This is the method that I've seen: a stick in the ground, and then checking the shadow at different times, and the longest shadow is noon, or shortest shadow is noon. And
it's almost something you have to infer,
right?
If you don't kind of know,
right? Yeah.
And of course, on a day like the solstice, it is in fact at noon, right? Noon local time. I think I'm going to go into that a little more at another time. So let's go ahead and see what they did to make it. Make your own quadrant. That's what they're calling it. Okay. With a simple device, you can measure the motion of the stars. Nice. It's a little messy. Glue the quadrant template to a piece of cardboard, then cut it out. Whoops. Tape a straw to the top edge over the dark stripe on the template. Make sure it's straight. Use a pencil to poke a hole through the circle. Okay, that's for the string, I bet. Poke the end of the string. Yep. Tape it down the backside. Tie or tape the weight to the other end of the string. And how you use it. Here's how to use your quadrant to find the latitude of your house. Did we get a comment?
Yes. Cliff says, yeah, down here, no pointer in the sky for us. But we have the Southern Cross and the pointer stars. Alpha and Beta Centaurus.
Oh, okay. That's good to know. So you can use the sun, but that's a whole different process. So, let's see. You need a clear night and a place you can see the stars. Start by finding the Big Dipper. Yes. And because there's 2 pointer stars in the Big Dipper, it will in fact direct you to Polaris, the North Star. You close one eye. Okay. Yes. Look through your straw. When you have it in sight, have a friend write down the number the string is hanging over.
Yeah, because you can't really see the string when you're looking through the straw.
Well, and it's probably going to require something like a red flashlight so your friend can actually see that number. So they gave you a template. That's cool. Take the reading 2 more times, then add the 3 numbers together and divide by 3. This is your latitude. That's interesting. Take the 3 numbers together and divide by 3.
Yeah, you're basically adding extra observations to make up for the sort of low accuracy of the device that they created.
Okay. So let's see. Yeah, and you know what? One of the things I found is that if you put your address into a site like Heavens Above, it'll give you latitude and longitude. That's kind of fun. You can also use your quadrant to measure the motion of stars over the course of a night or throughout the year. That's cool. All right, what else do we have here?
I don't know. You're the one who lined them up.
Yes. So here's a little video, and I'm going to play this one for you. Professor Rambling in Engineering. Okay.
But he knocks you out with chloroform.
An interesting. This is an interesting initial premise. Somebody knocks you out with chloroform. Yay! And you wake up. Where the hell are you?
You wake up. You're in the wilderness. It's dark though, and you can see the sky. The first thing you want to know is where you are. Can you figure out your latitude? Find the Big Dipper. The 2 sort of outer dipper points are pointing towards the North Star. You go directly down. That tells you where north is. So, okay, now you have an idea of the direction. The number of degrees that the North Star is above the horizon is exactly your latitude. And you don't need any fancy instruments. You could use your fist. Your fist at arm's length is roughly 10 degrees. So you go from the horizon, how many fists to get up to the North Star? So here it'll be about 3.5 fists, roughly 35 degrees. So you have some idea of what your latitude is. This is just showing, if you're near the ocean, and let's say near Hawaii, the horizon is given by the edge of the ocean. It would be about 2 fists because that's only around 20 or 22 degrees latitude. That's what you should do. You should try it. But he knocks you out with chloroform.
All right. So you can come back to both of us. So that's kind of nice because we've talked about, and I have a wonderful chart. I call it the fingers, and it gives you things like spread your hands. It's kind of like 20, 25 degrees. I forget. Your little finger is 1 degree across. And the basic idea is to hold them at arm's length. And we have talked about that before.
Yeah, so, because apparently just your fists in your arm length are kind of average out. The ratio averages out for most people.
Yeah. So I thought this was interesting too, because I also did some searching on Google, and this is sort of new to me, this AI overview. So we're going to be seeing some kind of general information at first when we go to search these things now.
Yeah.
And you can see more, and of course the normal search engine results. So I thought that was kind of interesting. DIY, measuring latitude and longitude, lots and lots of different resources for that. And yeah, how to determine your altitude. Oh, altitude. Oh, this one is kind of wild because, well, let me just go. Let's see. Is it over here? There's one of these. I think here it is. Altitude versus elevation. Well, isn't this interesting? Because there's like kind of a difference in altitude. I think it has to do with, yeah, the distance between, vertical distance, they say, between an object. In this case, they show a little balloon, and the Earth's surface, whereas elevation, the vertical distance between an object and the standard mean sea level. And I think they use, let's see, which is it? Altitude. Altitude's for planes, like
right.
We're 30,000 degrees, 30,000 feet above the planet, and that's our altitude.
Or
right?
Yeah. Or 10 kilometers if you are in most of the world.
Speak the rest, yeah.
But
so And here's another piece of it, like where, like if you think Mount Everest is the tallest mountain, it, maybe because there's things like the Earth's surface is, in fact, in some places below water.
Yep.
So I didn't realize this was sort of a variable,
Right. So
more of a variable number than anything.
yeah, altitude is above the Earth's surface. So if you're Mount Everest, your altitude is very high. Now, for aircraft, they always measure altitude at above sea level.
Well, that sounds like elevation then.
Right. It's just they decided that they weren't going to deal with the fact that a hill changes your altitude. So,
well, you sure care if you're in a plane heading toward a mountain. Let me tell you that
right.
much.
Well, you do want to keep some separation, but you also don't want the airplane going up and down every time you fly over a hill.
Okay, yeah, that makes sense. So I think you're gonna want to read this because there's a lot in here, and where in fact is this surface?
Yeah, and
Depends.
so I'll just say right now that their use of altitude to the Earth's surface is kind of pedantic, because for most uses it's to sea level. I mean, most uses are aviation, so it's sea level. Now, if you're in a balloon that doesn't go very far laterally to the surface, Earth's surface is a good measure because you want to know that you're 1,000 feet up versus 10,000 feet up. Because it might make a difference.
And landing on water probably isn't a great idea. Then they introduced this geoid word right here. Sea level is constantly fluctuating. I mean, think about it. There's tides, high tide, low tide, and can vary at different points on the world. This is why experts have to calculate a standard mean sea level, which is the average height of the entire ocean surface.
Which is what aviation uses. And they didn't need a special word for it, but hey.
Okay. So I do want to look into this a little bit more because this week was kind of crazy. So look for another episode that will probably include some other things as well as more details on how to do this. Yeah, it sort of like depends. So very, very interesting. And how to measure elevation. They actually do have like ways to do it here, and these are great WikiHows. They can help you find out about almost anything. Instructable is also a good resource for that. How to find? Do we have a comment?
Yeah, Cliff says the Hawaii island chain is taller than Everest, just underwater. Yep.
Yeah, they were talking about that. Yeah, here we go. Mauna Kea, an inactive volcano in Hawaii, has a peak that is just 13,802 feet above sea level. However, much of it is hidden below sea level. So this is 33,497 feet.
Yep. And there are some very tall mountains that don't even break the surface.
Oh. And then there's the mountain on Mars, which blows them all out of the water, so to speak.
Well, of course, because it has very little gravity to pull it back down.
That makes sense. Yes. So they do cover how to find your height above sea level. So let's see. They talk about these 3 points, 3 benchmarks in the area, look around the plot of land, search for benchmarks or objects that have consistent elevation. Yeah, things can change. Yeah, land settles. How sinkholes can make a difference too. If you're measuring the elevation between 2 different points in your yard, try using the elevation of your house as a benchmark. Same height. Set 2 metal posts between 2 different points. And I think they're going to be something about the tops of them. I did look through this, but I haven't read it thoroughly. Tie a string between them to determine the slope. Okay, take the end of a string and tie it securely around the post. Unspool the string as you continue along until you reach the second post. Snip off the string and tie it to the second post. When you do this, make sure that the string is as taut and straight as possible. Now you could, tracing. Okay, now you measure between the 2.
Yeah.
All right. And measure the post itself. Start where it enters the ground, stretch the tape, reach the top of the post. Write it down. You want to write it down.
Mm-hmm.
Make sure both posts are the same height. If either is taller or shorter, make adjustments as necessary. Okay. And looks like you hold it level. So let's see.
This is a very complicated way of doing this. Once you're done, I'll tell you an easier way to do it.
Yeah, see, I need to read through this better too. Go ahead. Explain
Okay.
what you think is easier.
The easier way just needs a little bit of math.
Yeah.
You want to measure the height of a building or a mountain or whatever. Go on the leeward side of, go on the opposite side of where the sun is, so that you can measure where the shadow is.
Okay.
And then you have a standard length pole. Let's do a yardstick or a meter stick. A meter stick. Yeah, a meter stick. You stick that on the ground, measure how long the shadow is.
This sounds like what the Greeks did.
Yes. It's what the Egyptians did. It's what the Greeks did. So you measure that shadow and you get the ratio of that shadow to the stick.
Mm.
Then you measure the shadow of whatever you're trying to measure back to the thing. So
I like
the peak of the house's shadow back to the house. And then you just basically multiply it by that ratio. And boom, you've got it. Just a little bit of math, division and math.
It's like a lot of things. There's a variety of ways to actually solve the problem. I am going to run this because we've talked about this before, and I think this makes a really good demonstration video of this measuring altitude, angular distance.
Yeah.
Yeah, go ahead.
Cliff says most sky apps have a lot of data on your exact location and height above sea level. Yes.
I was kind of hoping to figure out how to do it without any of the fancy, because of course, when I first became interested in it, I didn't have any of the fancy stuff.
Yep. And if your batteries die.
Yeah.
Well, okay.
Or if somebody knocks you out.
Yeah. The best use of your cell phone is to figure out your Latin lawn before the battery dies, right?
Call, text, something. Help.
Well, actually, you might want to do that before you call. Because how do you know how to tell them where you are?
You make a good point.
Help, I'm somewhere. Or help, I'm at Latin Lawn, this elevation.
Another one.
Come find me. Yeah. Oh, especially if the app can control a telescope, which most do now, and are mostly free.
Yep, very good stuff. So this is pretty good. Now, measuring altitude, yeah, it's kind of the same idea in regards to, well, I'm just going to run it. Here we go.
So you need to measure the altitude of an object that's in the night sky. Well, let me show you an easy way to estimate the altitude of an object. See the moon in the distance there, and we want to know what is the altitude of the moon right now. So we find the horizon, that line that kind of represents the flat part of our surroundings, and we take our fist and hold it out at arm's length. So as far away from your body as you can, at arm's length. And then you line your fist up with the horizon, and you put your other fist on top of it. I'm not able to do that right now, but imagine that I took my other fist and set it right on top. And then you take your other fist and set it on top of that. And each fist represents 10 degrees of sky. So I would say this one is probably, looks like 10, 20, 30, and maybe half a fist. So 35 degrees altitude is the moon currently. Hope this helps you estimate altitudes of objects in the sky.
So bring it back to us. That's kind of a different thing than I was really hoping to learn about, because I really wanted to find out my latitude on Earth. But that's also a useful thing, especially when you're trying to describe something like I use it a lot for something like sundogs, and you can kind of measure with your arm and your hand, different things, fingers. Like I said, that page I call the fingers. that's what I use to describe that to someone. So here, look for this in the sky, and it's in this position. We got another comment.
Oh, Yummy.
Hey.
Yummy says, that looks like fun. I'll try this. Yeah.
Yeah. All right. So let's see. I do.
Yeah.
Oh, there is.
Yeah, I actually try the I actually use the fist thing a lot when looking to see how high things are, because it's just a really easy, simple way of, not not totally accurate, but gets you in the ballpark.
Yeah, and I think of things like if you're camping or if you're hiking and you want to know when's a good time to stop and pitch your tent, you could in fact equate time with these angular measurements
Mm-hmm.
and say, okay, I don't want to pitch my tent in the total dark. When should I start? And you can do the measuring thing and kind of think about, I think it's about 15 is it 15 minutes per degree?
Mm-hmm.
Something like that. But that's another conversation.
Mm-hmm.
I do have one more I would like to show.
Okay.
Go ahead and
Oh,
put it back
you
on.
want to actually show it?
Thank you.
What a concept.
All right. This is kind of fun, and it's from a Hartzell propeller. The science behind altitude and how it's measured. While you're cruising through the skies watching your altitude, did you ever pause to consider how altitude is measured and why there are so many different ways of measuring it? We have, and we've got the answers to all your altitude questions. There's several types of altitude measurements, okay, which I've kind of already found out.
Well, in an airplane, you need a passenger who has a radio.
Okay.
And he just calls out the seconds as he's falling. When he stops
What?
calling out, you
What?
just do the math on how fast he can fall and how many seconds have happened, and now you know your altitude.
So they say there are different types of altitude measurements used in aviation. I did not realize that.
That you can only do as so many altitude measurements that way as you have. Depends on the size of your airplane and how many passengers it holds.
Okay.
And how many radios you have.
All right. So the altimeters measure definitive altitude and use a barometer to measure atmospheric pressure. Okay. Higher up you go, the lower the air pressure. That seems kind of normal. And this is why a pressure altimeter, really an aneroid barometer. So this is kind of fun. We got kind of the technical terms for these things is used to measure aviation altitude. There are, however, various other ways of measuring and referring to different types of altitude depending on the country and or conditions you're flying in.
For that, it's why as a pilot, you always have to set your altimeter
before
at
you leave.
Ground level. Yeah. And you set it to the elevation of the location that you're on.
That makes sense. Okay.
So, and different times of day, because air pressure changes depending on heat and stuff like that. So it loses. So basically you have to set it, even if you land at the same place, you might have to reset it in the next morning.
Interesting.
Not by a lot, but by a little bit. You might need to tweak it.
Okay. So this is a lot more involved than I ever realized until I did the research for tonight's episode. All right, so let's see. Indicated altitude refers to the reading on one's altimeter when the altimeter has been set to the local barometric pressure, like you were saying, at mean sea level MSL. Whereas absolute altitude is the actual distance the aircraft is flying from the ground. Okay, so we've got this, let's see which one is.
Because the way the
actual absolute versus what is it?
Barometric.
Barometric. Oh, it is barometric. Okay.
Yeah. And the pressure one is good because airplanes fly differently at different air pressures.
Okay.
So knowing what altitude you are from that can tell you basically how long you can fly before you run out of fuel.
Oh, that sounds useful.
And also what speeds you should be going, because the speeds change based on that. So that's very useful. The absolute altitude is useful for like not running into things.
Oh, so and okay,
That's the splat distance.
and so they have true altitude here. Is that more like the barometric pressure, or is that something else?
No, it's
Measuring the elevation above mean sea level.
yeah, it's measuring above sea level, but it's using electronics usually instead of pressure,
Mm.
because you could have higher low pressure areas at different heights. No, not like you won't have a low pressure at high altitude that's lower, or a high pressure at higher altitudes that's a higher pressure than sea level, but it could be high or low relative to what it's supposed to be at that altitude.
Right. Different things happen in the atmosphere that make it expand and contract.
Mm-hmm.
So that sounds like I would. Okay. Let's see. Oh, they talk about hot climates.
Yep.
Or high elevations.
Make lower air pressure, yeah.
Well, they say density, altitude.
Yeah. Okay. Which is air pressure, essentially.
Okay. Which corrects the latitude readings for non-ISA International Standard Atmosphere conditions like these, taking into account pressure, humidity, and temperature.
Mm-hmm.
So there's a lot more to it than I ever thought there was, and I really loved finding out this by reading this article.
Yeah. And there's a
So
little
go back to us. That's all. That's what I got here.
Yeah. There's a plastic thing that looks like a slipstick. What's the real name for slipstick?
A dipstick in your oil
no,
or something?
No.
No.
For calculation before calculators. Slide
oh,
rule.
slide rule.
So yeah, the thing is, for aviation, you've got a slide rule with a spinny thing on it.
Yes, I've seen that tool.
Yeah, and it's been way too long. Oh hell, 40 years since I last flew. So I've forgotten a lot of that stuff. But yeah, you can calculate all of that with that.
And Janie says, thanks for the conversation and curiosity produced results. More to learn. Absolutely.
Yeah.
Again, like I said before, I think I will probably do another episode on this topic because this week kind of got away from me and I got an ankle issue. I know there's a lot more as well, like the elephant toothpaste. And I'm sure a lot of people are very familiar with vinegar and baking soda that react together. But I think you know about that one. I want to talk about other things. But yeah, there's lots more out there, I think. So we'll discover it another day.
Bleach and vinegar, bleach and ammonia make a big combo too.
No, don't do that. Please don't do that.
Pretty
stop. Do this. This right there in front of you.
Last pretty color cloud you'll see.
No, there's no.
Oh no, that one's
colorless and odorless.
That one's colorless. And
I saved someone that once upon a time did that.
I have a cousin who worked for someplace where they said, if you see a green cloud coming up over that building, call your family and tell them you'll help you. Yeah, because bye. Okay, June 27th.
No.
Oh, some stellar events this week. Yes. Well, I was going to get to it. I was just going to flip them.
Mm-hmm.
Maybe. June 27th through July 4th.
Careful.
Yeah, makes Jamie.
I'm very tolerant too.
Makes those things. Yeah, well, she's saying very careful for my health from stuff that I do, or very careful that you don't hurt me.
Yeah, that's where I went. But yeah, you're right. Yeah.
Yeah. My sniffer doesn't work, so I don't play those games anymore because I'll never know.
No.
But June.
I get stuff out of the fridge and go, "How are you still alive?" Because those smells fine to me.
Yeah, the first couple of weeks after she moved in were interesting. I lost a lot of food.
Did you?
Perfectly edible food.
No.
That, when the pork gets this rainbow sheen on it, that's just pretty.
Mm.
And beef, if you rinse it off real good, it gets less slippery.
Got it.
But,
please proceed. Where are you at?
June 27th, Mercury and the Moon are in conjunction.
Trinitrotoluene?
Oh, that's probably the green one.
Oh, I see. Okay. Thanks, Cliff.
June 29th, Mars and the Moon are in conjunction, and Mars is 0.2 degrees south of the Moon, and an occultation is visible from most of North America and Western Africa. And Regulus.
She told you there was an occultation for that one.
Yeah, Regulus is 1.5 degrees south of the moon. June 30th, the moon is at descending node.
Oh, TNT, right. Trinitrotoluene.
Oh, yeah.
Got it.
Okay, yeah.
Cool. Thanks, Cliff. Not the green cloud. Okay,
No,
good.
nitroglycerin, just the stuff that you don't want to trip if it's in liquid form when you're
Yeah.
holding it.
Right.
Um,
Did you read that one?
and you don't make more than a thimbleful, Cliff. That's how you keep your hands.
Yeah, I know people who do this. They count their.
Yes, yes. I have a whole bunch
That
of
might apply
buddies
next week
that,
too.
that do finger checks.
That might apply next week
Yeah.
too, actually.
Yeah, and then someone comes back on. Ned comes back on later after a few weeks, calling himself Three Finger Ned. June 30th, moon is at descending node. Oh, I did that one.
You did that one, okay.
Rerun. July 1st, moon is on the equator, and it's Canada Day.
In Canada, probably.
Probably only in Canada would be my
Probably.
guess. But for some parts of the world that include Canada,
We did not drink the beer that's in the fridge, honest.
that's probably going to be there for a really
Probably.
long time. Ended up with one. We'll probably have it forever
Yeah, could be.
because I don't like the smell. I don't even care what it tastes like. July 2nd, first quarter moon. July 3rd, Earth is at aphelion, furthest from the sun. And Venus and Uranus are in conjunction. Also, Spica is 0.8 degrees north of the moon. July 4th, Independence Day here in the US.
Yay.
Probably not celebrated so much in England. Just a guess.
Or Canada.
Yeah, I don't think Canada
Or
cares.
Australia.
Yeah,
Anywhere
I don't
else.
think those guys care. England doesn't really like it so much, but they probably don't care anymore anyway.
Yeah.
I don't think there's anyone alive who cares.
No.
And on the 4th, the moon is at apogee. Also, Mercury is at greatest western elongation, 26 degrees east of the sun, and it rises before the sun, which means that you get to see it. So if it rose after the sun, you wouldn't be too bright.
The idea is go looking early morning.
Yes,
There you go.
before sunrise,
Yes.
which sunrise is kind of early morning for us, especially in the
Or
summer.
late night.
Especially in the summer. In the winter, not so much. July 4th is also we'll do our Friday night show. We'll celebrate Independence Day and talk about fireworks. Find us Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page, maybe, and the Everyday Spacer YouTube channel every time.
So far. What inspires you the most for the coming week? If you or someone you know has done something interesting involving space exploration, science, astronomy, we'd love to share our life. Join us again next Friday, July 4th. Jeff will talk about fireworks and what makes their colors.
Yeah, so
And I got some ideas about that too.
so Cliff, we'll talk about pretty boomies.
Pretty boomies.
Okay.
Yes.
Boomies are pretty anyway,
Yes.
but fireworks are even prettier boomies.
They're pretty on like a show. I don't want to see real boomies in person. Thank you very much. So, all right. Anything else from you?
Nah.
I'm sure I'll have more, but I'm going to do a different episode about that. We're going to do a shout out for people. Thanks so much for being here, Cliff and Jeannie and Naomi.
And
And Scott was here. Oh, wait, I didn't see Dawn. Did she?
Yes.
Dawn
Oh,
here?
Dawn's here. Yeah.
Dawn's here?
Yeah.
Oh.
She came in at the very
Oh, yeah,
beginning.
there she is. And we said, Naomi, good. Again, it's always a better show when you're here. Give us great comments like this one. Oh,
All right. Naomi says,
oops, sorry. I did it too.
thank you so much, guys. Have a great night.
Thank
You
you
too,
for
Naomi.
being here. You have a great week too.
They won't let us have fireworks. Well, we can't actually have homegrown
No,
personal fireworks here in California because
suppose.
they don't want the state to burn down.
No.
But that's
Yeah,
just
that
too
is
bad.
illegal. However, people still do it. I think we
Yeah.
heard something the other night, didn't we?
Oh yeah, yeah.
Mm.
Someone had a
Yeah.
big firecracker last night.
And lucky
But-
for us, we actually get to see a fireworks show this year again because they will have it in Moore Park on July the 3rd. And apparently, it's a cheaper show to do it on July 3rd. And it's great for us because it's not July 4th when we're doing our show here tonight
Yeah.
on that night.
Yeah, this time we're happen to be doing our show during the time that they do fireworks, which actually somewhere close enough you might actually hear some during the show.
Yeah, that's
Um,
true.
Although sometimes they wait until 9:30. I don't know how long we'll actually go, but
Thanks, Dawn. Have a great week, folks.
Yep.
We're so glad you're here with us. We are going to go, though. Good
Yes.
night.
Good night.